All right, let's get started. So today's lecture is a kind of an interesting meta-level paper, trying to look at the question of whether all of this work we're doing in verifying systems actually leads to more correct or more reliable systems. So the question is sort of an empirical question of, are these verified systems actually correct or not? And what might go wrong to make them not correct. And of course, the story we've been trying to discuss this whole class is the premise that if we can actually verify a system, this means that there's perhaps no bugs in the parts that we've verified. That's a super high level view of this story. But of course, there's a lot of caveats to it, including the tools and exactly what verification is done and what it means to have no bugs. And this paper takes a very empirical look at this. They really look at a couple of systems in the distributed systems category, which is why we're reading this paper now in this class. So in fact, this paper looks at one of the systems we already looked at, Iron Fleet, which, if you remember, is this work from Microsoft on building a verified distributed system using Daphne and TLA. And in addition to Iron Fleet, this paper also looks at two other pieces of work that came out in a similar time frame a couple of years ago, a system called Verdi, which is also a replicated state machine system developed in Coq, and another system called Chapar from several authors at MIT that at the time that developed a verified key value store that ran over multiple machines. And the interesting thing is that these guys actually do find bugs, despite the fact that these systems are verified. And there's bugs in sort of, as we'll look at, in what the authors call shims below the verified code. And there's bugs in the specs in terms of what the system purportedly satisfies, as well as bugs in the perhaps tools themselves, whose job is to check these proofs, to have the computer check the proofs for us. And these are somewhat serious bugs. So the authors find that these bugs can actually violate the supposed guarantees that we wanted these systems to have. Guarantees, and sometimes crash the process or the server that is running this supposedly verified code, etc. So it's kind of an interesting result. At some level, as we dig deeper, it's not going to be terribly surprising that indeed the verification story has some limits. But the thing to take away from this paper is really kind of a qualitative case study, like what actually goes wrong in practice and what can we do. Like the thing to keep in mind is what should we do to avoid the likelihood of falling into the same pitfalls that these verified systems fell into. Like fell into is maybe over claiming, and there's a couple of bugs, and probably still fewer bugs than an unverified system would have had, but nonetheless. So maybe let's start by trying to understand how is it possible for a verified system to have bugs. Well, we're going to have some kind of verified code that we're going to be doing proofs about. So here we go. But it doesn't exist in a vacuum. The verified code, probably in the case of labs assignments, as you are super familiar with by now, is sort of a thing sitting in your Coq source code that you can use to generate maybe executables. So there's probably some correspondence between this verified code that you're verifying and actual executable code that your system is going to be running. And even the executable code itself, you're probably not verifying the entire thing that you care to execute. So that probably is going to sit on some kind of a shim layer that is going to connect your executable code to some kind of an operating system underneath. And probably there's hardware underneath of that. So a reasonable size software stack below your verified code that gets run at execution time. And there's probably things above. So there's some kind of an application that the user might be interacting with. And in order for the verified code to deal with being sort of one piece in a bigger puzzle, we rely on specs. We specify these layers. So we're going to specify this layer, and we're going to specify this layer. And the layer on top of the verified code is what we've been traditionally calling the spec of the system. So that's what the system is supposed to satisfy. That's the abstraction it provides to the higher level, or it's visible. But the verified code also is going to run on top of some platform, in this case, an operating system with a shim layer on top of it. The shim is mostly there to just sort of invoke the right OS functions that the verified code is going to rely on. And here, these guys are going to also kind of take a form of a spec of the underlying OS, but typically these show up as some kind of an axiom in our verification process that describes the primitive operations that are available to us and the properties that those operations have, so that we can build on them. And these axioms, of course, better be correct. And in some sense, the spec also has to be correct in order for the application to use it in a sensible way. So what's going to happen is that there's going to be some kind of a user or developer sitting on top of this, and they're going to be using or developing this application, and they might actually look at the spec and try to understand, am I writing application code in a way that correctly expects the right things to happen from this executable chunk of code in the middle? So the nice thing is that verification hopefully is going to check that this thing between the yellow lines is good, but the things below have to satisfy the axioms, and the thing above have to rely on the right properties. The developer has to correctly understand the spec being given to them. So that's one part of the story. That's one part of the sort of reason why verification isn't all encompassing. We're just sort of plugging in one layer in the stack that you're running. The other part of the story is that the verification itself is done by probably some kind of a reasonably complicated tool. So as the paper finds in these projects, there's probably some kind of a build system, or I'll sort of loosely call it that. So something that you're going to invoke as part of checking this verified code for correctness and compiling the executable code from it. And there's a lot of sort of tools. The paper calls these auxiliary tools. And somewhere in the middle, inside of this build system, one part is actually the Verifier Core. So something like the inner kernel inside of Coq or Z3 or some other theorem prover or checker that is ultimately responsible for deciding if your verified code meets, I suppose, the spec under these axioms. And as this paper finds, there's sort of bugs in this tooling as well. So the verifier, lots of people try to make the verifier reasonably small or hopefully reasonably correct. But the wrapper around the verifier is much less carefully studied because it's a one-off thing developed for a particular project as opposed to being sort of a widely used tool like Coq or Z3, and as a result, slightly buggy. So that's sort of the picture, maybe a slightly different take on what the paper also shows in figure 1 to give some sense on where the bugs are coming from in verified systems. That make sense? Any questions so far? All right. So let's try to understand how these guys actually find bugs. It seems like kind of a hard question or like a hard thing to do in some sense. Indeed, it's a pretty tricky proposition that these guys are actually signing up for. So these guys really do a fairly hands-on, study. They look at the code, they look at the design, they experiment with it, and they actually spend quite a bit of time trying to find bugs. One useful thing that they do that actually turns out to be pretty effective for them is fuzzing at the shim layer. So what's going on here is that they look at this shim layer below the verified code, and they try to run the system and inject sort of all the possible executions that the shim layer could allow. So they run out of memory, they try to fragment messages, etc., and they see if the executable code actually handles this correctly. And as it turns out, sometimes they don't, if the axioms are maybe not quite accurate enough. So fuzzing turns out to be a useful plan. Another useful plan is maybe cross-checking the shim or the implementation against other sources of sort of truth about what the system should be doing. So a number of sort of general purpose approaches, if you will. But at the end of the day, it's just a serious effort. Lots of time spent carefully looking at these systems, and perhaps others as well, where they didn't find bugs maybe, trying to see whether verification really works well or not at the end of the day. Make sense? Questions? All right. So in some sense, there's not as much in this paper in terms of sort of big, techniques or sort of constructions that you have to know about. So it's more, I think, a case study, as I was saying before. So we'll look at these bugs and try to understand what is it that went wrong, and maybe some advice or like try to extract some lessons. What could the system developers have done to avoid having these kinds of correctness issues in their verified systems? So to that end, let's start with Iron Fleet. So this is a system that is hopefully relatively more familiar to you guys from the paper a couple of weeks ago that we had. So this, if you remember correctly, Iron Fleet provides a replicated state machine abstraction. And then on top of a replicated state machine, they implement some things that sort of run inside of this RSM box, including, I believe they have a counter and some other examples. But the sort of software stack for them is, in terms of tooling, is relatively sort of tall in a sense. So they have the Iron Fleet code itself, and this thing is written in Daphne. And then this Iron Fleet code gets passed to the Daphne tool, which is used to both compile it and check the theorems. Daphne itself builds on an earlier or lower level project at Microsoft Research called Boogie. And Boogie itself builds on a proof checker called Z3. There's a fairly, serious stack of software here, and these are serious, developers writing Daphne and Boogie and Z3. But it's a complicated stack, and it turns out that indeed the authors of this empirical study paper found some serious issues here. So in terms of the categories that I mentioned earlier, so the paper sort of proposes that maybe there's bugs in the shim, sort of below the code, or the spec above the code, or the tooling. So one sort of surprising thing or sort of interesting thing is that there's no shim bugs that the authors found in Iron Fleet. And I think this is a reflection of Iron Fleet actually being a fairly low-level verification. What I mean is that they're not building on top of a whole Linux operating system or sort of big abstractions like that. They're actually implementing things down to a fairly low level of abstraction themselves, where they don't actually need particularly complicated shims, and they got their shim abstractions or specifications or axioms correct. So that's pretty cool. But there are actually some interesting spec bugs and tooling bugs that we're going to talk about. In some sense, maybe I got my check marks and X's backwards here, depending on how you interpret the X or the check mark. But indeed, there are sort of spec bugs and tooling bugs that we'll talk about in Iron Fleet. And it's kind of interesting to see what a tooling bug looks like. So the tooling bugs mostly stem from the fact that there's sort of this complicated stack of software that's responsible for checking the proofs of Iron Fleet. And in fact, there's another tool here called New Build that the Iron Fleet developers use to orchestrate the whole process. It's like the make equivalent of the Windows world for Daphne code, I guess, that they used. And what's going on is that New Build, it's kind of like a make file whose job is to invoke Daphne, which calls Boogie, which calls Z3, to both check the proofs for Iron Fleet and generate the executable code at the end of the day. So New Build, calls Daphne and sort of propagates all the way down the stack. And there's sort of three bugs. The paper numbers them all I2, I3, and I4. So the tooling bugs all end up being of this sort of interesting flavor where it's mostly there was an error, but the errors get ignored. Kind of a surprising category of bugs, but this is what actually ends up going wrong several times in this Iron Fleet build system. And maybe the easiest thing to see is So one of the bugs involved new build. So new build is responsible for running Daphne to compile this whole stack. And new build has a script to look for potential errors in the proof. So the way this works is that new build is going to parse the output and check for errors. And what happens is that the new build script, as far as I understand the paper's description, only looks for the first, only sort of checks the first line or the first message that comes out of the Daphne build. And the result is that in some situations, Daphne itself prints an error message, prints some kind of a warning message that new build looks at and says, that's all fine, that's not a problem. And then there's other messages that are produced by Z3, like Z3 crashing or having some other problem. But the new build script just ignores those error messages and declares success. And then actually continues to build sort of Iron Fleet. So that seems pretty damaging in the sense that new build produces an executable, and it sort of purportedly checked the proof along the way, but the script to check the proof had a bug. And even though the check might not have gone through all the way, the developer or the person building the source code is none the wiser, doesn't realize anything went wrong. So that seems like an interesting problem, sort of maybe not one I would have expected if I were to sort of try to understand what would have gone wrong. And there's sort of another interesting bug in a similar sort of overall category where what happens is that Daphne itself, so this you might imagine you could sort of think of as a bug in the new build script whose job is to sort of check the output of this whole stack. Daphne also, manages Boogie and Z3 itself. And one problem in Daphne was that it didn't actually properly handle all the possible errors that could have come from Boogie or Z3. And the particular bug that the authors discovered is that Daphne ends up by accident ignoring Z3 signals. What I mean by this is that if Z3 is killed by some kind of a signal, then depending on which signal it was, Daphne might not actually think that's a problem and continue running. So what might have happened is that maybe the developer was building Iron Fleet and it was taking a while. So the developer just hit Control-C on their keyboard to kill this process, and Z3 gets killed, and Daphne sees that it got killed by a signal, but didn't have the right code to check for these signal error cases, and doesn't notice that Z3 was killed and didn't finish properly. So seems like it could have been a problem. Ends up being not a huge deal because in this case, when the developer hits Control-C, Daphne doesn't get around to actually building the full executable, so at least doesn't produce a executable file corresponding to an unchecked piece of source code. But still sort of reflective of the importance of really making sure the whole proof has completed successfully, as opposed to just looking for errors. So this is sort of the flavor of the bugs that the authors of this paper discovered in the Iron Fleet build system. Any questions so far from what you guys read in this paper? So how to avoid these bugs? Any thoughts? You guys, well, let's suppose, are in charge of building a system that verifies some code. How would you try to avoid falling into this problem? Well, I'll sort of try to say a couple of things myself, but feel free to chime in as well. So one way to look at these problems that the Iron Fleet developers run into is you can sort of see that in many levels the build system was looking for some kind of an error to be signaled to indicate that the proof didn't go through. So one way you could have maybe decided to phrase this is to, instead of looking for errors, maybe ask for a very positive confirmation from the build system itself, from the proof checker like Z3, that all the proofs have checked out. So maybe really you should have some sort of a positive check instead of looking for errors. So this way, all these problems like you didn't see the error message or Z3 got a signal, all would have resulted in Z3 not printing the message that indicates successful proof checking. It's maybe easier said than done. So, Daphne is a complicated system. There's many times when it invokes Z3. So who knows if all that if there's really a single place where Z3 completes verification. But nonetheless, sort of structuring things in around a positive way might have helped. Another is probably you really should test. So test the whole tooling for proof failures. So maybe an important part of your overall system should be that you have some source code that is known to not meet a certain specification, and your build system should try to build that software, and you should make sure that you're actually observing that certain software cannot be verified. And this way you can actually ensure that if a problem does creep into your real software and the spec isn't met, then you have some more confidence that this will really be caught. So that seems like also probably a good practice to follow. Maybe another comment is, make the proof checks more integral. So a common pattern that you see over and over is that code that is not sort of on the main path and doesn't get tested all the time is going to have bugs. And you can sort of see maybe this being an instance of it. So to the extent that your proof checking workflow is the same as the workflow used to generate the code that you run every time, will perhaps ensure that your proof checks are happening all the time and problems will be noticed quickly. So that's sort of one angle of on these sort of tooling bugs. Does that make sense? Any other thoughts in terms of what might be useful to avoid these kinds of tooling problems in verification? One interesting thing that the paper sort of mentions is that they found these bugs in the tooling itself, but in the sort of these auxiliary tools, but they didn't actually run into issues in the Verifier Core itself. And that's not to say that bugs in the Verifier Core don't exist. So even Coq, which has a relatively small kernel whose job is to check proofs, has had bugs in the past where you can just prove false in the Coq proof system. And in the lecture notes, there's actually a URL where the Coq developers very carefully keep track of all these bugs because they're super important to them. But it's like a surprisingly small set of bugs, and the Coq developers take this extremely seriously. So there's some reasonable chance that if Coq checks out your proof, then pretty likely to be correct. And these are not bugs that are everything just proves correct all of a sudden. These are bugs where like using a very specific construct in Coq might accidentally be computed incorrectly, and you might be able to prove false. But it's a quite unlikely combination that your software has a bug and the proof of that software somehow tickles a bug in the proof system that says that your software is correct. So that seems to work out pretty well. Z3, which underpins things like Daphne and Boogie here and the Armada system we looked at, certainly a larger piece of software, and I think it's had many more bugs where you might accidentally prove false compared to a system like Coq. But even there, I think the same insight also applies, that it's relatively less likely, not super likely that your software bugs somehow line up with a bug in the proof checker where that bug lets your buggy software be verified correct. Somewhat of a hand-wavy argument, of course, but nonetheless. Other questions? Any other questions? All right.
So quick comment.
Oh yeah, go ahead.
Sorry, on the Daphne bug, I actually don't remember the details, but I found the bug report I shared in the chat. I think it's actually just exactly what you said. We're just trying to do Control-C, and then Daphne actually printed verified. And I don't remember whether it affects code generation. My guess is actually doesn't. So you actually will still get the binary because definitely will just continue run, and code generation and proof checking are separate, two
Oh
separate
yeah,
topics.
potentially. Yeah, I was sort of assuming that Control C might have affected the top level new build process as well. But I guess it really depends on what new build does, and maybe if you're running this on a Mac with Make, maybe something else happens.
This one is actually inside Daphne, so it's not new build. It's the Daphne
Oh, I see.
process
Daphne
itself.
itself. Right. Yeah. Makes sense. Interesting. I should actually introduce Shi as well. So he is one of the co-authors. He was the advisor of the students that wrote this paper. He's been auditing this class for fun during his sabbatical.
Never, graduate. So
He
still
was our former student at some point. But yeah, so yeah, feel free to ask questions. And if I don't know something, maybe she remembers as well. Although this was a little while ago now, but
yeah, I don't
nonetheless, yeah,
remember
thanks for
much.
coming. Yeah. All right. So so this is covering some of the tooling bugs that the authors found in the Iron Fleet paper. They also have an interesting bug that they discovered in the Iron Fleet spec itself. So this is in the Iron Fleet. There's a bit of a spec ambiguity where, not super important whether this is a bug or an ambiguity or misunderstanding or who knows what, but not so much to figure out who to blame, but an interesting aspect where really illustrates the subtlety in getting these specs right. So just to sort of draw out a picture for you guys, so Iron Fleet is trying to implement, let's imagine, some kind of a key value store using replicated state machines. So the abstract view of this is that we have a table with keys and values, and this table is populated, and various clients can issue put commands, put key value, and maybe get commands. This is just to give you a sense of why you might care about replicating a key value store. And internally, what's going on is that Iron Fleet would probably run many replicas of this key value store on various machines. So here's the RSM machinery underneath each replica, whose job is to keep the replicas in sync. And then each of these replicas has its own copy of the key value store running on top of it. And the challenge here, or there's like a bit of a tricky corner case to get right, where what if one of the replicas goes down, or replica fails to reply? Or from the client's perspective, the client issued a request, let's say a put, but it actually hasn't heard back what the answer was. So at the logical level, you might want there to be one clone. You issued a request, it's going to go into the table, it's going to do the put, and you'll get the result saying, yes, your put is done. But internally, what might have happened is that maybe you sent your request to one of the replicas, and that request got lost, or maybe the replica crashed. Well, at this point, you might want to resend your request, the same request, to a different replica, in hopes that that replica will finally do your request for you. And the problem is that, if you retransmit, are you going to get duplicate execution? Because it might be that your request got lost, but it might also be the case that your request made it just fine, and it's the response that got lost. So in that case, if you already put KV and that value was in the database, then retransmitting it again will cause you to set the key to value V a second time. That might actually be bad if others already saw the value and put something else in its place. You'll just keep overwriting the key with your value, which means that your put happens multiple times. So the ideal goal, I think most sort of system developers would agree, is to have some kind of an exactly once execution. Which means that if a client submits a put operation, then this put happens exactly once, not 0 times if you keep retransmitting, and not multiple times. And the way you get this is you dedupe. So you assign some kind of a unique identifier to every request, and then if a replica gets a request, it needs to check whether some other replica already executed the same operation. So easy enough. This is a fairly classic thing that distributed systems do. And here's the interesting thing in Iron Fleet. In Iron Fleet, they actually had the code for deduping, for basically filtering dupes. So they were doing this. But the spec did not promise it. So the end result is that actually the authors of this paper went into Iron Fleet and they deleted the couple of lines of code that were responsible for duplicate checking. And it turns out Iron Fleet still proved correct according to the Iron Fleet spec. So here's an example where there wasn't actually a bug, but the spec was actually weaker than what the implementation provided in this particular respect of exactly once execution. So this is a subtle issue, and takes, I think, quite a bit of effort to try to look at the spec and understand what it says. Entirely possible that there's other bugs in the other systems that these guys studied that they just like didn't get to, because it takes quite a bit of time to look for these things. So it's really cool that here's an example of really a spec, and not a bug in the code, but a bug in the spec where could have had a mistake, or maybe in the future Iron Fleet could have accidentally broke this dupe filtering and not realized that this was the case. The reason I say ambiguity here, and the author sort of also mentioned this ambiguity issue, is that the Iron Fleet developers thought, well, maybe actually that's fine because we don't want to necessarily promise the duplication. And the fix by the Iron Fleet guys was to add a comment saying, yes, this is what the spec really means, as opposed to changing the spec. But nonetheless, highlights the importance of the spec being precisely what you mean and precisely what the application developers expect that are going to be using your verified component. So this is the example that these authors found in Iron Fleet. There's actually probably other bugs that other spec bugs that we've seen in previous systems that we've looked at in this class. So for example, the NetCore system, the verified SDN controller from last lecture, we didn't talk about this extensively, but if you remember, the NetCore spec really talks about input packets. And actually the spec has nothing to say about output packets at all, which, this is kind of the same thing as in Iron Fleet. Their example SDN controller doesn't do anything terribly horrible. It actually sends the input packets to the expected output ports. But the spec doesn't talk at all about the output packets at all. So it would have been totally fine for their verified SDN controller to drop all packets, or alternatively broadcast them on all output ports. And that would have been totally fine by the spec, which is kind of weird. So the spec is a little bit weak compared to what you might have expected. And maybe an example closer from our own research is in FSCQ, the verified file system that we at this point looked at a number of lectures ago. We're actually pretty lax, about error codes. So the spec basically says, you can return any error code you want if there's an error. That's partly because we were, maybe lazy or thought that there's something else seemed more interesting to try to specify. But indeed, this is one place where the spec of the file system is maybe quite a bit looser than what POSIX says. And actually, the SibylFS guys, the file system checking paper that we also read, they actually ran SibylFS on top of FSCQ. And they found lots and lots of cases where FSCQ returns nonsensical error codes. And they filed lots of bug reports with us. And, reflecting the fact that we didn't really spec it out to begin with, these are not sort of bugs we cared about deeply in some sense. We probably could have fixed them. But indeed, these are sort of discrepancies where if you wrote an application that was expecting error codes along the lines of what POSIX intended or said was going to happen, then FSCQ, despite being verified, would not have produced the right error codes, and maybe your application would have done the wrong thing. So that's sort of perhaps an undesirable situation. Maybe a more interesting case is also in a later work in DFSCQ when we introduced fsync system calls. It turns out there's no universal agreement on exactly what fsync or fdatasync should do. We picked something, but some other application developers might not have expected our choice of fsync behavior or fdatasync behavior, and would have been bitten by this. So it's important that the spec really pins down what the app developer wants to do. All right. So what do we do about, how do we avoid spec bugs? Any thoughts? Suggestions? So many of these things, right? Like, yeah, go ahead.
Oh, so I guess I was just going to say that, like, in this case, is there anything more than you can do than just to make sure that your spec is not ambiguous? I mean, like I feel like it's kind of just like you have to think really hard about what you want to
Yeah,
represent.
so I should say, like, you know, there's like quite a different flavor to these questions than what much of this class is focused on, right? Like for much of the class, we have clear answers. Like if only you do this hard thing and verify some theorem, you will just get a definitive answer, man. And these questions are really kind of heuristic things where, well, you know, what you do to, you know, lessen your chance of these bugs. That's a very different flavor of a thing. And you're exactly right that at the end of the day, there's nothing that fundamentally can help you decide that you're absolutely have the right spec. But there's maybe some good ideas. So I think it basically boils down to taking the spec as an artifact and trying to do something with it to make sure that it's correct. So, you know, you should take the spec, and one possibility is maybe you can prove an app on top of the spec using the spec. And what I mean by this is, you know, if the Iron Fleet guys wanted to go ahead and prove even like a toy key value store on top of their spec, and maybe they wanted to, like, you know, so suppose they wanted to implement a counter on top of a replicated key value store, they would have proved something like, well, you know, I do a get, I increment it by 1 and I put it back. And then someone else does a get, increments by 1, puts it back. You know, probably like almost the simplest thing you could do. They would have probably quickly discovered that actually they can't prove that the result is going to be incremented by 2 because this original put from the guy that incremented by 1 first could come in and overwrite the put that increments by 2. So I think being forced to use the spec to prove an application often exposes whether your spec is strong enough for the application needs. Similar to netcore, right? Like, so in netcore, the spec says nothing about the packets that are going out of a switch. So if you actually took netcore and you try to prove that all the packets get sent to an auditing server, you'd probably quickly discover that actually nothing at all talks about what packets get sent to anywhere at all, let alone the auditing server. And then you'd probably figure out, okay, well, maybe I should change the spec to add this so that I can prove my little example. So I think one really good idea is to use the spec. And one way to use the spec is to prove an application using on top of that spec, not looking at the implementation, but just the spec itself. So this way you couldn't rely on the fact that Iron Fleet just happens to have done the duplicate filtering correctly. It's just the spec doesn't require it. Another category of using the spec is you might actually try to prove properties about the spec. I'm not sure if, well, what I mean by properties is in contrast with proving an entire application, maybe what you should prove is really that, you know, certain invariants hold that you should expect from a spec. So for example, in a netcore system, maybe what you should prove is that the spec says you will never have packets looping forever, or I don't know, maybe that's a property of certain configurations in netcore. Or maybe in Iron Fleet, you could prove that if clients stop issuing puts, then the system will reach a quiescent state. That might be, you know, true or maybe not true if you sort of have these retransmissions coming in and the system keeps applying the puts even though the clients have long gone home. So I don't know, you know, there's various properties you could imagine. I think there's maybe not sort of an obvious invariant to check in the examples I've shown so far, but nonetheless, perhaps the best example I could find from the things that are on the screen is maybe an FSCQ. Like a property you probably would want to state is that if your system call for any file system operation returns an error, then the spec says nothing changed. That's probably a good thing for your spec to tell, because otherwise the application is going to see the error code and probably it's going to assume that nothing changed. It'll be cool if the spec promised this. So this is the kind of a property you could try to prove about a spec. That's really about a spec itself, not about the implementation. And SibylFS tries to do something similar, if you remember. SibylFS also does this property check for POSIX. or for their model of POSIX anyway. These are sort of, heuristics, if you will. I don't know, maybe it's a little bit better than just a heuristic. There's some ways to gain confidence in the spec itself. And probably the last thing that's sort of a good thing to do with a spec is to, test or cross-check this thing. So kind of like what SibleFS does, where they check lots of file system against each other, or they have one specification and they check whether the specification makes sense by running it against many file systems. So that's one other way to sort of gain confidence in a spec. And the sort of intuition there is that if you have multiple implementations of some spec, then probably they're not all buggy. In fact, probably they're pretty good. And if there's a disagreement between the spec and the implementation, could easily indicate that either the spec or the implementation is bad. So it's worth finding discrepancies between the two, even if it's just a sort of a randomized testing. Anytime you find discrepancies is going to be useful for you. And the SibleFS guys, I think, both found bugs in the implementations, as well as found that their spec was maybe a little bit fuzzy or not quite right for some file systems. Make sense?
In general, I think a couple of other things. One is that many of these examples demonstrate that although often it's necessary for specs to have non-determinism, it's a dangerous thing, because it's very easy to overlook the fact that the spec might have so much non-determinism that the system doesn't have to do any of the things that you think it's doing. And the other sort of much broader remark is all of these things are evidence reinforcing the general principle that you want the spec to be as simple as possible. Because as Nikolai is saying in various different ways, there's fundamentally no way to be sure that the spec is right.
Yeah. So
because what are you going to judge it against?
Right. Yeah. So almost sort of coming back to this picture, I guess the one, so this is the picture we saw at the very beginning, like one way you could avoid these spec problems is to sort of lift up. So one sort of general strategy is to encompass more of the world in verification. And to the extent that's a realistic answer, then it's probably worth verifying more, but of course comes at a huge cost, because sort of verification all the way to machine checked proofs is quite a serious effort, as you have all seen and experienced now. And sort of even more of a question of how good of a boundary are you picking, as opposed to how much code are you subsuming in the verified box. So maybe even an argument is that you should really aim for narrow, clean boundaries, as opposed to trying to verify as much as possible. So it might be a good idea to really not verify maybe even as much, as long as it lets you focus your spec on a much narrower waist, either below in this axiom sense or above in the spec sense of what your system is providing at the end of the day. So it's absolutely a good point. Yeah, so the simplicity of a spec is crucial, since there is no fundamental way for you to check if the spec is right, and sort of judicious choice of the layer below or above your verified component could make a huge difference here. And you sort of see this in one of the other systems that these authors look at, Verdi. They seem to have chosen a pretty wide API for the system below them. And as a result, they have a number of interesting bugs in the sort of in the axiomatized specs of their underlying primitives, the shims.
Another point that might be worth making is that I'm not sure that any of the systems that we study in this course have made any attempt to prove anything about the performance, to specify anything about the performance. And of course, in practice, you very often run into situations in which the system satisfies the functional spec, but it's actually useless. Because
that's true, yeah. So yeah. So like in some ways, there's like a huge non-determinism gap, even in terms of performance itself, or liveness, or like having tight bounds on. Well, maybe it's a little bit overreaching to bucket it as non-determinism, but sort of, yeah, I think performance and resource consumption are important.
Sometimes there are misunderstandings about this. It's certainly true that in principle, any of the schemes that we have been studying in this course are capable of specifying and proving things about performance. But it's very seldom that you actually do that because it makes things quite a bit more difficult.
Right. Yeah. There's a couple of papers that we are not haven't assigned in the schedule, but that try to look at this. But they're somewhat theoretical yet. I think we're pretty far from practical techniques for really proving that, or even having concise specs for what performance should mean.
One amusing anecdote to add to this discussion, which is I heard the story of a paper that verified a property about a programming language. So they verified that all well-typed programs have some nice property that you'd like. And then it later turned out that there were no well-typed programs. It was impossible to construct a program in this programming language. So in that case, it would have gone very far if the authors had written just one example. And I think that's just generally true for a spec. Like a lot of these specs have like lots and lots of assumptions and lots of stuff that is general. Boiling that all down to one example is very valuable.
Yep. A more maybe immediate issue that we run into in our research is that often what we prove is that the system operates sort of in steady state, and every operation it takes, it can take its own current state and evolve it and sort of do the inductive stuff. But it's very easy to accidentally assume something impossible in your invariant, and then as long as that impossible thing holds, you can keep making progress, but you can never initialize your system. So it's important to initialize your system, which is maybe a slightly different take on Tej's example, but indeed, like using a spec, crucial, absolutely. Yeah. All right, so these are sort of spec bugs, and I think there's lots of, it's worth paying quite a bit of thought to how are you going to construct your spec so that you can check it and try to use it and to cut it at the right level so that you can hopefully make it concise and simple. So let's switch gears and look at another system. So that was Iron Fleet, which had no shim bugs. It was just this spec ambiguity and some tooling bugs, which is, I think pretty impressive for the system of that complexity. Another system that actually has very similar aspirations is Verdi, which is also a replicated state machine proven in Coq instead of Daphne. And the way Verdi works is that you have the Coq source code, and they use extraction, very much like we suggest that you guys do in labs, to produce OCaml code. In labs, we do Haskell for no deep reason. And then this OCaml code is going to be linked with some shims. And you can think of these shims as basically just little wrappers. And in case of Verdi, these are wrappers for TCP connections or some kind of network abstraction, and for the file system. And the TCP connection is used for communicating with clients and servers and between servers. And the file system is used below to store the state of one of these replicas in case the replica crashes and needs to reboot. And sort of interestingly, there's a whole flurry of bugs that the authors discovered in the Verdi shims. So the spec seems okay, or the authors haven't found any sort of big issues in the spec for Verdi, but the specification of the API on which Verdi is built turns out to have been sort of a little bit of a mismatch between what OCaml shims are providing and what the formal spec is in Coq for these shims. So it's kind of interesting to see what these bugs look like, just to prime your thinking about the kinds of issues you should be on the lookout for if you're trying to do this for real. So here's an interesting issue. Verdi assumed that receive always returns complete messages. So the setup is you got one replica, and here's another replica, and this guy is going to issue a send, maybe sending some large message like even 8 kilobytes. And what's going to happen is that, of course, the send is going to go into the kernel, and the kernel is going to send out packets going to the other machine. It's going to send out, 1, 2, 3, a couple of packets, because 8 kilobytes can't fit in one packet. And on the other machine, you're going to call receive, and you're going to return some message up to the application. And what Verdi's axioms said is that if one machine sends a message, then the other machine, when it calls receive, it'll get the next message. So it'll get the next 8 kilobyte message. As it turns out, TCP doesn't really guarantee this. TCP is a stream instead of a message sequence. So if it turns out that maybe this packet arrived on the destination host when the receive was called, then the receive will actually return a partial message. So it'll return just the bytes that arrived in this yellow packet and will not return anything from there because it hasn't seen them yet, and will not wait because there are no message boundaries in TCP. And this, kind of, I guess if you think about it carefully, not surprising that this can lead to all kinds of bad things. Could have, led to arbitrarily bad things. This particular case caused the implementation to crash, if I understand from the paper, because, the theorem said, or the axiom said, you'll get 8 kilobytes at this point. So they just go and look for the 8 kilobyte, data. And if it's not there, OCaml probably throws some kind of an exception and kills the process for accessing objects out of bounds. So it's not arbitrary memory corruptions like buffer overflows in C, but still the process terminates and stops running. So kind of undesirable. So that's one example. They have another sort of even maybe more embarrassing example where they actually have incorrect marshalling. So the first example here, V1, is really about sending sort of byte sequences from one server to another and not having the whole byte sequence when you receive it. This other bug was really about sort of some kind of a client talking to a server, and not sure about the details. Maybe she can fill in the exact details, but it seems like there's not just a TCP abstraction that Verdi was relying on. It seems like Verdi was really relying on some kind of a command abstraction. Maybe these are the 8 kilobyte commands that Verdi was assuming that you could send all at once. But what was going on is that the client was able to send some kind of a command, and maybe actually multiple commands altogether. And the way that the shim actually implemented this was that it actually sent the commands separated by new lines. So I'll demonstrate this by having a \n in here. So there's just a list of commands, one per line. And on the server side, when you get a command, maybe this is the receive operation, this detail I'm a little bit fuzzy on, then the server's shim would split the input messages by new line and give them one at a time to the server as separate commands. The problem is, of course, that separating things by new lines is not so great if your command itself can contain new lines. And this could be the case if you're implementing a key value store where your value could include a new line. If it's like an arbitrary blob of bytes, sure, you could have a new line in there. So this encoding scheme was not actually a correct encoding scheme for arbitrary payloads, for arbitrary commands that you could inject here. And indeed, if your command, like suppose that your command was put key 5 to be the value hello new line world, well, the way this would get encoded is that the shim would take your command, put k5 hello new line world, add a new line to it, and send it on. On the receiving end, the receiver would parse this as the first command and this as the second command. And things aren't going to work out so well. If this looks like a real command, then all your commands are going to be one-off, and things are quite broken at that point. So important to have robust libraries here and maybe narrow abstractions. So this seems like a thing where fairly straightforward cock proof could have proven that you have a good marshalling plan, but for whatever reason, Verdi did this in the shim layer itself, it seems like. Make sense? Any questions about these bugs?
Line breaks in the arguments.
Sorry?
It's probably just like even simpler, probably line breaks in the arguments.
Yeah, like the command itself is probably fine, but indeed the arguments could be arbitrary byte sequences, and then I
think Iron Fleet spent a lot of effort proving those.
Yes, this is the thing that I was pretty impressed by, is that Iron Fleet really goes down to a much lower level of abstraction, I think, than Verdi did, sort of comparing the two. I think Iron Fleet has a verified network stack in quite a number of ways, and coding and crypto and so on. all done, sort of verified in Daphne, which is pretty cool, and I think pays off. You can see that indeed verifying more means fewer bugs in those verified components. So in some level, this is sort of a testament to verification does actually help you avoid bugs. Right. Other questions, comments? So, these are sort of bugs on the network side. Verdi also had sort of interesting bugs on the storage side as well. So Verdi used a file system to store its state for replicated state machines to recover if individual nodes crash and reboot. But again, they sort of axiomatized the file system interface. So like file read-write operations. That turns out to be a complicated thing to axiomatize correctly if you're worrying about crashes. So here's one example. It turns out that they were assuming that large writes were atomic, but actually large writes are not atomic. So what this means is that what actually happened is that, as far as I can tell, is that you have one of these replicas. It saves its state. So it issues a write call saying, I don't know, maybe write 100 kilobytes to disk. And then after a crash, you have the same node that tries to read the data from the file. And the assumption or the axiom that the Verdi developer stated about the file system interface basically said that read should either return either 0 kilobytes or 100 kilobytes in this case. It's either going to be all there or not there at all. And this is not actually how file systems operate. Totally possible to get some prefix of these writes to be on disk after a crash, or maybe even some, random subset of the blocks being on disk, depending on how aggressive of a file system you're using. But in any case, the assumption turns out to be a bad one. And what the authors discovered of this paper is that this could lead to these Verdi nodes not being able to resume at all after a crash. So what happened is that you tried to write 100 kilobytes, but then you crashed while doing so. And then after a crash, you try to read, and it's only a partial checkpoint or a partial log that you wrote. And when it reads it in, it's not well formed, and something goes wrong in the OCaml code, it crashes. So your machine crashed and rebooted, and now Verdi can't recover, and your system can't start again because of this bug. So authors point out that actually in this case, there's no data lost. You could actually go back and manually fix up this file by sort of deleting the partial write. That was possible. But then they sort of discovered another issue in Verdi, this V4 bug, where the Verdi actually has an incorrect plan for writing snapshots. And what happens in Verdi is that I think what's going on is that you're running a replica, and there's actually multiple files. So there's maybe an old snapshot that contains your state, and maybe you wrote this guy a while ago, and now you're writing a new snapshot. So here's a new snapshot. And one operation that the replica had to do is, update or write a new snapshot and then delete the old snapshot. Seems like a sensible operation. At some point you do want to move your snapshot along, except that the way they did this, or I should say, the axioms they had about the file system were pretty strong. They basically said, if you write a new snapshot file, it's there. So now it seemed totally sensible to go delete the old snapshot. Except this is not actually quite what the file system guarantees, that if you write a new file, it's not actually on disk yet until you call fsync. It's actually still sitting in memory or in some disk write buffer. So if at this point you call write on a new snapshot and then you go immediately calling delete afterwards an old snapshot, you could end up in a state where the old snapshot is now indeed deleted, but the new guy hasn't made it to disk fully. So in this situation, you could actually, after a crash, end up in a situation where the old snapshot is just gone, but the new snapshot is only sort of there partially. So now, if you go and read this guy, well, this thing is corrupted, and there's no old snapshot to read either. So that seems like an unfortunate situation to be in. So again, this boils down to making the wrong assumptions about what the file system interface is providing to you, and as a result, sort of writing code that doesn't work out so well. Make sense? Questions about this bug? So there's two more bugs in Verdi. Verdi is full of interesting cases to talk about. Not to say bad things about it, but Shi, you wanted to say something?
Actually, sorry, that was me, I think.
Yeah, go ahead.
I had a question, kind of like in terms of answering like how you might deal with like the fourth bug in this case. Is there any work like with the like x86 TSO for giving like very formal semantics of what's expected out of like operating systems, like or like
yeah,
the
this
systems
is like
calls?
a very fruitful. Yeah, I think trying to specify operating systems and file systems in particular. There's a number of papers in this style. Almost like every research group that's working in the space has written a paper on this. So we have a paper on formalizing DFSCQ, which is our sort of higher performance FSCQ variant. And we have one particular spec for a file system. Shi Wang and his colleagues have another paper that appeared in ASPLOS, where they also look at how to formalize the behavior of a file system in a slightly different way. There's several groups some group from Australia that's also cooked up a file system specification trying to formalize that. There's some PLDI papers coming out, I think, or actually no, a POPL paper, I think Tej was telling me, coming out this year maybe, that's trying to formalize what the ext4 file system actually provides. And in some ways, it's a fairly messy endeavor, the closer you get to real file systems, because these specs were not designed to be super clean. I'm not sure actually the developers were thinking of it in these algebraic or sort of formal terms. That's not necessarily anything sort of trying to say that they should have done that, but made sense at the time. But if you try to formalize the exact behavior of ext4, you end up with a fairly complicated model, which might actually be not quite right. The more complicated it gets. But indeed, I think people have tried quite a bit to formalize file systems in particular because they have sort of important properties on crash. There's also some work from researchers at Wisconsin that have tried to understand, maybe not formally in the sense of this class, but they've certainly done a lot of work trying to understand what properties various file systems do or don't provide. And partly because they're not doing it formally, they're able to look at many more examples and sort of sketch out these properties much quicker and much more, understandably to a reader, perhaps, in some sense, in English prose. But also an interesting example of how different file systems in Linux also provide actually quite different behavior. And if you really aim to support the lowest common denominator, there's not a whole lot you rely on. There are some things, but yeah.
Okay, cool. Thank you.
Yeah. So it's like, actually, I've said this several times, but I want to say it again. I don't want to blame the Verdi guys necessarily for getting this wrong. I think it's like a whole open problem for how to spec this file system out right. So it's not surprising that there's a bug in there, but it's mostly an illustrative thing that this is the kind of thing that can go wrong if you don't get the spec right. There's a couple of other bugs that Verdi ran into. One interesting case was they actually have a bug where they fail to read the snapshot. Here's a situation that happened for them, which is that they had a node and they actually had a snapshot on disk and they called read on it, and read actually returned an error. And their assumption or their axiom about the file system interface was that if read returns an error, the file is not there. That's not quite right. There's other situations that might cause reader to return an error. And in particular, if you have lots of files open, the operating system might say you're out of file descriptors or out of other kind of resource, maybe you're out of memory or something else. So there's other errors that could cause this read to return and not give you the data. And their spec was not quite right. And as a result of this, they sort of assumed that, well, there's no snapshot, so that there is no data to read from the snapshot. And as a result, they lost some state that was in the snapshot that they should have actually read. So seems undesirable. So it's important to really get all the corner cases right for the axioms that you're building on, because could easily translate into bad assumptions. And maybe the sort of trickiest thing to figure out in Verdi was actually this interesting thing where they ran out of stack space. So what was going on is that they wrote some recursive code in coq. So this is a function, I think it was called find greater index. So it's a function that they wrote in Coq, and it got translated into OCaml. And very much like you do in Coq, this was a recursive function, and it did a lot of recursion, and it was kind of inefficient. So it was sort of had a linear stack depth because it just recursed a linear number of times with respect to some argument, roughly speaking. And OCaml has, actually pretty much every system has a fixed stack size bounded by how much memory you have at some level. And this recursive function exceeded it in some situation if you had a particularly long log to traverse, and caused your replica to crash. And it's a weird situation in a sense, because if you think about Hoare logic kinds of specs, the Hoare logic specs often allow this, because Hoare logic specs only talk about termination of functions. So if you have a Hoare logic spec and the function never terminates, for example, it crashes in the middle because it runs out of stack space, the Hoare logic spec does hold. Namely, if you ever do return, the post condition will be true. But if you never return, so be it. So this is a weird situation where the spec is really weak in terms of guaranteeing progress or liveness or something else going on. So total completeness instead of partial completeness, total correctness instead of partial correctness would have been a stronger specification. Then you would have been required to demonstrate that you definitely will return, as opposed to something conditional if you return. So this is a kind of interesting bug where it's not even clear what's the right approach to try to avoid these issues, other than sort of testing, or as Butler said, really trying to focus on a much more precise notion of performance and really your expectations out of the system. Make sense? Questions about this family of bugs in Verdi?
I think that one, the interesting part of it is the one single client. You could just wait for a long time. Then you could just go online and you could just bring down all the servers. And that's if the client crash itself, that's fine. Like, who cares?
Oh, you mean this like V8 bug?
Yeah, the last one, yes. It's actually because of the servers, all the servers are trying to construct a snapshot to send to the client. And that thing turns out to be too big. So the server crashes instead of the client. So if the client shoots itself, who cares?
Yeah, so there's like, if you look at the, indeed, an interesting part of this paper is trying to understand like how bad do things get because of these bugs. And indeed, this one has an interesting flavor that she is pointing out, which is that various servers, first of all, it causes the server to crash because the server runs out of stack space. And in fact, then if one server crashes, the client will fall back and go talk to another server, and that server will then crash, and so on. And all the servers will eventually crash. And if you combine this with some other bugs, well, maybe once a server crashes, it never recovers. And well, that's it for your replicated state machine. So kind of an interesting, indeed. Mathematically, if something goes wrong, then that's it. You don't have any guarantees. And indeed, it could actually end up this way. Like even a relatively small combination of relatively few bugs could get your system into pretty serious trouble. Interesting to see this play out in an actual case study here.
It might be worth pointing out that a much less formal version of this problem, of this phenomenon, is something that large-scale cloud services have to deal with all the time. Whenever they deploy new versions, they always do it in a very conservative, we'll deploy to a few guys first, and then we'll deploy to more guys, and then we'll deploy to the whole fleet. And they have elaborate provisions for backing out new versions if it turns out that they don't work well enough. Of course, there's nothing formal about the process I just described, but it has very much the same flavor as what Nicola has just been talking about.
Yeah, so probably a good lesson to take away from this is that formal methods aren't really a substitute for many of these holistic whole system operational things, and they probably go hand in hand in practice, because formal guarantees probably don't extend to every property that you care about at the end of the day. But nonetheless, useful to have some formal guarantees in some contexts. All right, so the last system that this paper talks about or studies is Chapar, which is not a replicated state machine, unlike Ironfleet and Verdi. So Chapar was done by Mohsen Lassani, who was a postdoc at MIT at the time, and Adam Chapala, and some other colleagues, if I remember correctly. So these guys actually wrote a key value store, so directly a key value store, instead of having a key value store be a side effect of running it on top of a replicated state machine. And it's a particularly interesting kind of a key value store. It's some kind of a causally consistent key value store. So what I mean by this is that the replicated state machine approaches we looked at in Verdi and Ironfleet have an extremely tight specification saying that if you talk to any replica, you'll always get the latest answer and it'll be correct as if you had one copy. That's all great. But in practice, another kind of key value store people do run is not super consistent between replicas, but some sort of a loose replication protocol. So if you talk to one replica, you might see newer or older versions of the same data than if you talk to a different replica. And in order to achieve some semblance of sanity in this universe where you don't have strong consistency, people have cooked up this notion of causal consistency, which is somewhere in the middle between nothing or eventual consistency and strict consistency. And causally consistent basically says if you have sort of one key that you look up and then you look up a different, if you do a put and a get, they are sort of causally related. Or if you observe one thing, then you'll observe things that happened before that get. So some kind of an interesting property. So it's not just an RSM. And for the purposes of sort of this discussion, it's based on UDP. So unreliable messages being sent between replicas because they thought, well, why not? Let's go lower level. So at some level, it seems like maybe a good plan to assume less of the underlying system. But it turns out they had actually quite a number of shim bugs. Well, I guess 3, fewer than Verdi, but they're kind of interesting, or in some way. So the first bug they had was that their axioms about UDP assumed that there were no duplicates possible at UDP. So as you can imagine, this caused basically the same problem that I described to you guys about Ironfleet key value store earlier. So if you can issue a put operation on a key value store and the UDP protocol can duplicate your put, well, your put can now happen multiple times, and that could cause your value to sort of come back from the dead. You thought you overrode it, but no, it's back because UDP duplicates your packet. So that's possible in practice. UDP allows dupes, but the axioms that Chapar had about UDP said, no, it's just messages. They can't be duplicated. And indeed, their protocol sort of assumed this couldn't happen. And if you had a dupe, you could actually violate causal consistency in Chapar. So that seems unfortunate. Another bug they had was that they also assumed that UDP had no drops. So again, UDP of course could lose packets, but if a packet loss happens, then Chapar would basically lock up because no one would bother retransmitting a message, and the servers would just sit around waiting for that message to arrive because it's got to get there. So important to get these axioms right. Another sort of, well, these you could sort of think of as basically they got UDP wrong in several ways. Slightly different flavor of a bug they had is that they really used some kind of an odd OCaml, well, not an odd library, but there's sort of odd semantics in the OCaml network library. So what was going on was that they were using an OCaml library to marshal messages that were going to be sent over the network. And the bug was this strange thing where if you try to send a message that was too big to fit in some kind of a packet buffer, then this OCaml library will give you an error back saying, yeah, I couldn't fit your message in the network buffer. You go figure out what to do next. That seems sort of okay enough. But then actually what happens is that part of the message that you tried to send and failed is still left in the network buffer in this library. Seems like a weird library at some level. So then what happened was that if Chapar tried to send a message but failed, maybe not a disaster yet, but then it tries to send the next message, and the next message sort of goes and reuses part of this buffer. So the next message is intermingled with some discarded parts of the previous message, which just ends up corrupting the message in all kinds of strange ways, as you can imagine. So this really seems like, the OCaml library has some confusing API that was hard to use, and the Chapar guys, of course, fell into the trap of not being able to use this complicated API or confusing API or formalize it in the right way. So it seems all sort of tricky to get right. So it's important to try to figure out, like, well, these shim bugs, how do you avoid them? So at some level, right, like these shim bugs are similar in spirit to the spec bugs we talked about before, because they're both spec and shim bugs. They're both specifications about some piece of code, and the spec is sort of an axiom. How do you know if it's right or not? You just have to sort of gain confidence that your spec is right for the system in question. But the sort of flavor of what you can do, I think, is going to be a little bit different here. So one sort of general strategy is to expand the boundary of verification. Ooh, what happened to maybe my external program crashed here? Seems like it. Can restore the file. All right. Let's hope that doesn't happen too many times again. So one thing you could do in order to sort of avoid these shim bugs is try to grow the verification boundary. So encompass more code in the verified code part of your system. So we talked about a bit about this earlier in the spec bug context. But in some ways, it's also sort of important not just to expand the boundary to be as big as possible, but really have a narrow waist or API, because narrow API means a simpler spec or a simpler axiom, and more likely that you'll get this right. So I think this OCaml library sounds like a bizarre library. This is just the opposite of having a simple, narrow API that you cut against. So probably would have been better to either verify to something that's like below this library or above this library, but just like this layer seems like the wrong thing to try to formalize and cut at. So that seems like a good general plan. The other thing that maybe to avoid spec bugs is to really sort of make the spec more general. So spec should really include all the error cases and resource uses and so on. So it seems important to get right if you want to deal with errors happening in this shim layer at runtime. Another sort of thing to sort of maybe realize is looking at this, right? These shim bugs probably would have led to pretty much the same bugs if you were to write unverified software. These shim bugs, the way you think of it is really they're stemming from a misunderstanding of the developers that are trying to use this API. So if you were to write Chapar as just an unverified OCaml program, and you misunderstood the UDP API, like here, or you misunderstood this complicated OCaml library, you would probably make exactly the same mistakes. So these shim bugs aren't really unique to verification in a sense, even though they have a pronounced effect in verification. So the way to think about it is like it's really have a, shim should really have like a clean API, and you should use well-designed libraries. Very much like using a good library probably would have avoided these bugs if you were writing unverified code too. So all those considerations sort of come into play here. And then sort of the last probably thing in this category is to sort of test the shim itself. So things like SibleFS, you could probably apply similar techniques. And in particular, you should test, corner cases. So things like, out of resource errors, etc. So this is where the fuzzing technique from the paper's authors really shines well, where you see that being able to inject random errors is pretty effective at checking if the implementation or the spec for the shim layer captures all the problems that could arise at runtime. Make sense? Any questions? All right, so maybe just to sort of conclude, what are the lessons learned here? So probably not the right lesson to learn that verification is useless, even though we see that verification is sort of fallible. The cool thing from this paper is that actually in the verified code, they did not find bugs. So they looked quite a bit, but the verified chunk of the code really was bug-free, even though it's tricky stuff. It's distributed systems code, which is pretty error-prone. So verification does seem to be useful, but you really need to pay attention to the fact that verification relies on some serious assumptions. And it's important to be cognizant of these assumptions and do the right thing to get these assumptions to work out well. So at the top level, you got the spec. In the middle, you got the tools. And at the bottom, you have the shims that you're building on. And roughly the things that the paper sort of suggests and that we've talked about here is that for the spec, you should probably try to use it and make sure that it satisfies the properties you want out of it. For the tools, probably the right strategy is sort of extensive testing to make sure that you actually check that tools can report failure. And the shim underneath of it, probably, fuzzing it is maybe the only bit of sort of concise advice other than the sort of general advice of making everything, including a spec and the shims, simple. So that's probably a summary of what the lessons to be learned from this paper are, roughly speaking.
I think it's interesting to reflect on the Amazon paper that we read at the beginning of the term in the light of this paper and think about which of these problems, if any, the Amazon guys would have run across. Of course, their aspirations are very, very different from those of the systems that are being attacked in this paper.
Mm-hmm. Yeah, it's probably a useful thought exercise. I mean, I sort of run out of time, so I probably don't have time to really try to, simulate this thought exercise here, but probably useful to think of it. It's also the case that maybe the Amazon guys are in a slightly unique position where they are really experts on the entire stack, and they really understand the shim, if any, underneath of them, and they understand the specs that they're trying to implement versus the research papers that these empirical studies looking at, where the researchers are experts on verification or on their sort of distributed system, but maybe not experts on the OS kernel underneath of them, or maybe applications on top even necessarily.
But also the Amazon guys have a very clear notion of what they're trying to get out of the formalization. And it's pretty much orthogonal to all these things.
That's true, yeah. So here we're sort of looking at some like, is this all correct? But the Amazon guys just want to,
they want to know whether
clear up their own thinking.
They want to know whether their high-level algorithm is going to work.
That's right, yeah.
They rely on other methods for dealing with all these other issues. Not that these other issues don't exist in their world, but they don't rely on formalization to attack these other problems.
Yeah, good point. Yeah. So yeah, maybe another way to think of doing a verification at different levels really helps you understand something about the code or the object, the protocol you're trying to verify, even if, or gives you some insights independent of whether there's remaining issues. Yeah. All right, so that's it for this lecture. I think that wraps up our distributed system section of the class. And on Tuesday next week, we'll start looking at security, starting with the Komodo paper, if I remember correctly. So see you guys next Tuesday.